Okay, so this is the database presentation, and before we jump in, I just want to set the expectation right. The intended audience is for really what you see here, so if you're on the advanced side, this is not for you. If you just want to know more about how databases work, you're a developer, or you're one of the decision makers doing inventions and things like that, this will be very useful for you. The whole idea of this started when Colin, one of our attendees here, had asked me the question of, why not just use a spreadsheet for your database? And I thought about it, and I've been working with databases for so long, and it never occurred to me that actually this is actually a real solution to a lot of databases, and a lot of people really actually use tab separated values or comma separated values for databases. But once things start to scale, it turns into a gigantic mess that is totally unsustainable. And the reasons you see here are really why you would use a database as opposed to just having it on a file on the disk. So I'll give you a second just to give that a quick read and let me know if all of this makes sense.
What's a blob?
A blob is a data type that is a large block of text. So for example, a blog article is typically stored as a blob. It's not just a big string, but it includes like new line characters and markup and stuff like that. You can also store pictures as blobs as well.
So you can
Okay, I see what you're saying.
All right, can I go to the next slide?
Yep.
Okay. In order to understand a database, you need to understand the level above that, which is the management system, or DBMS. The DBMS is actually what we're going to be talking about today because it's kind of just what people are referring to when they refer to a database. Typically, you're actually talking about the management system most of the time. And here we have common DBMS as per this particular ranking. And you'll see some names here. Some of them might be familiar to you, some may not. A database can be relational or non-relational. And a lot of them have this acronym SQL in there. Oracle.
Structured query language, is it?
Exactly, yeah, right on the money, Colin. That's right. Yeah, that's what it stands for. It's structured query language. And so a lot of these are quite similar. Some of them have more specialized use. For example, Redis here, even though it has a smaller share, is a database that exists only in memory. And so this is for applications where you don't necessarily need things to persist till the end of time. For example, holding on to user sessions on a website will typically be stored in memory. And that way it's very fast, but if the system powers down or you lose some data, it's not the end of the world. On the other hand, most of these guys here are all in the SQL sector. Even Oracle is actually SQL. It's just the proprietary flavor of what they're calling it. Over here we have the Stack Overflow Developers Survey, which had a sample of 50,000 people putting votes into, I actually can't remember whether it's for what is their preferred DBMS or the one that they're currently using. They tend to be quite similar. There is a reference there if you want it clarified, but essentially MySQL is by far king number one. Some people call it MySQL. It rolls off the tongue better. Both are valid ways of referring to that. Then you have Postgres or PostgreSQL. Another SQL by Microsoft, SQLite. All of these, the top four SQL. And as you go down, you'll see a little bit more similarities. MongoDB is a non-relational form of database. And I'll talk a little bit more about what the difference is afterwards. Redis, I mentioned, is your in-memory database, and then MariaDB is an interesting one. It's basically just a clone of MySQL. And so as you can see, SQL is really dominating the DBMS space right now, and that will be the focus of what we'll talk about today. MySQL is an open source project. It's very well documented, and it's used by many of the biggest companies in the world, many of which you probably see on a daily basis, like Facebook, YouTube, and Netflix. When a company says they use MySQL, it doesn't mean that everything that the company has that you see is stored in there. It might be a part of the website or even a small little section of it, something they're choosing to do with that. Or it could be the whole thing. But in most cases, these big companies will actually use a combination of different technologies, and MySQL will be one of them. MySQL's actually dates back pretty far. The relational database management system was kind of incepted before it could have been implemented on computers. It really blew me away when I was learning about this in school, that the logic and the whole idea of the database, was conceived of before anybody could build it. The project was acquired by Sun Microsystems for $1 billion. And Sun eventually had a downfall, and MySQL was a really strong thing going for them, and it didn't prevent that. But Oracle had the competitor. If you remember on the previous chart, we saw Oracle was one of the big ones. And one of the things Oracle did was they acquired MySQL. And for a period in time, the term MySQL was the de facto standard so strongly for implementing anything SQL related that the terms were used synonymously with SQL and MySQL. I remember learning about this back in the day, and it was very consuming. I thought, why do we have MySQL? What does that even mean? But ultimately, Oracle purchased Sun, and this made people very worried because Oracle was the opposite philosophy of what the original developers for MySQL wanted. They wanted closed source. Oracle had a history of making things proprietary, and people were worried that they would make MySQL not free. And so some of the developers left Sun Microsystems to create a fork of MySQL called MariaDB, with the mission of keeping it free forever. This may not have been necessary because Oracle never killed MySQL. It's still being developed actively to this day. And so it's just something to consider if you choose to use MySQL. And a fun fact is the person who named MariaDB was born on the same day as I was, and he has two daughters, Mai and Maria. So MySQL and Maria.
Wait, so MySQL is developed by Oracle?
MySQL, yes, yeah. As of now, they're maintaining the project.
Okay, but it is open
And
source.
they own it technically, but it's open source.
Yeah, they own it. I think they have some paid tier versions of the project, where you can maybe have them manage it for you or get some extra features, but the core of it is free and anybody can use it.
Okay.
Neat. Okay.
Okay. Or did we talk about this? Oh yeah, so MariaDB. So, or I guess MariaDB, I call it Maria. Yeah, so it was intended to be a full drop-in replacement for MySQL, and I've done this before. It works pretty good. It's like 99% similar to MySQL. There's a couple of things that were not ported over, but today it's very similar. Oracle does have, yeah, a closed source version, but that's kind of something else. You don't have to use it. And so there's a common debate. As a business, this might be a decision you need to make as whether to use MariaDB or MySQL. And so MariaDB has more contributors and more commits, and their feature planning is done publicly on a mailing list. So anybody can easily get involved with what is going to be added in. But some people would prefer to have the stability of a large corporation versus the open source community. It just kind of depends on your philosophy. But a lot of performance increases on MariaDB has made it more popular in recent years. And so that's kind of the debate, right? MariaDB has more support for storage engines. It's faster, has more features, but MySQL has more developers on staff. So I mentioned before, like MariaDB has more contributors, but MySQL just has a higher amount of hours of actual human labor going into the project because they're paying people full time to work on it. But if you choose to use MySQL, you're at the risk of maybe one day Oracle decides, you know what, all you guys, now you have to pay for it, and so you'll be stuck frozen in time if you don't want to switch over.
But in like certain companies, it's less philosophical. Like if you were like a healthcare company to go for this, that's like government run, to go on an open source versus like an actual true company, I don't know. I feel like you'd have to go with the true company, even though you're claiming it's the same. But like,
It's true. Yeah, you probably would want to have the support of a company, right? Rather than just being at the mercy of an open community.
exactly.
That said, there is a third contestant joining the fight now, Postgres, and this one is commonly considered by businesses. I've used it as well, and the main differences are that Postgres will be used in more critical level applications that need a guarantee of service. So government, healthcare, and banking will use Postgres because
Okay.
it's designed for that. It's designed to just be this bulletproof system that may not have the same level of performance, but you have a higher degree of durability within the database. And it also has a lot of features, and it's generally considered to be more complex than the other database management systems. And so that's the general gist of it. But then it's an open discussion because you might think that that makes it more secure, but because MariaDB is maintained by an open source community, it actually gets updates much quicker than Postgres. Postgres is also open source, but the community for it is much slower. And so, for that reason, actually, if there was a security hole, MariaDB would get it first. It's so which one's really more secure? It's open for debate. One more look
The fact
at
of the matter is, the debate is there because none of which are foolproof. They're all hackable at this time. By everybody, definitely not. By certain people, potentially.
I'm not sure if any of them are hackable. I think
Okay.
it's a layer. There's many layers to security, right? So if you want to hack a database, first you need access to the database,
You have
and
to fish for like staff, employee access codes and stuff.
exactly right. The security
Yeah.
holes that used to exist have all been patched now. You need to be really sloppy about your work in order to leave your database open to vulnerabilities like injection, where people can, write queries in the search field on a website or something like that, or in like the URL bar, and that actually executes on the database. These were the ways hackers used to do it, but nowadays when you're talking about security vulnerabilities, it's really obscure stuff that doesn't tend to come up so much anymore. But there's always new things that can happen. It's more like, will it be hackable in the future? And if it is, how quickly will it take? How long will we have to wait for a fix?
Okay.
So anyways, yeah, so we have here another comparison of these database management systems. And what I want to put into focus here are just some of the business related decisions that somebody might make in order to choose one of these. And there's another column that we'll introduce now called scalability. And scalability is very important when you're dealing with applications that are intended to grow. Mark Zuckerberg started Facebook on MySQL, and he ran into some very complex, interesting scaling issues to enable, 100,000 users and plus to use the system and make it actually responsive and work. And so today we've learned a lot from these kinds of challenges, and it's something you need to kind of think ahead a little bit. If you're going to make an application like that, you can scale a database vertically or horizontally. And vertical scaling refers to like having a more powerful computer that's serving the database. And horizontal scaling is where you have more replications of the database at the same time. And that way the load is distributed. Each of these has their own pros and cons. And I don't want to go into too much detail about it, mainly because it's kind of a little bit more on the advanced side when you really get into the details. But also in today's day and age, these things are changing so fast that it says here MySQL is vertically complex, but if you're using some of the latest operators and tools with Kubernetes to install these things, then it might not be so complex anymore. So it's something you just need to consider at the time that you're going to choose what technology you're going to use. You need to have a scaling solution, and it is important to look at, well, what are your options with databases? This might be actually the defining feature that determines, which one you end up using. Another item is documentation. Of course, things that are better documented will just be better for the development team to work on. And there's also SQL and NoSQL. I'll talk about that as well. And so, yeah, a little message on the side here, right? In today's software, right, really the most current stuff, we try to be as stateless as possible so that you can make replications and they work. But at some point, you do need to have data that persists, and scaling that will typically be the most complex part of your application. This is really the most difficult solution to solve, just because it's difficult to handle concurrency when you're dealing with data that's written to the disk. Okay, so non-relational or NoSQL. As you mentioned, Colin, right? SQL is a structured query language, and so you can kind of imagine NoSQL to be something that's just more free-form. You don't need to specify exactly what will go into a table of the database in order to have something that will take data, right? With NoSQL, you just sort of dump it in and it'll just eat it up. And so it's a lot easier to set up. And it tends to actually work better for data that just isn't structured by nature, or there's just so many columns that you actually don't want to set up all of these keys and things with what you're doing, or have connections between tables in order to make it all work. With NoSQL, it would make a great solution for a social media application, for instance, because you don't have to make everything rigid. And then the counterpart, relational, structured query language. You get the benefit of it being ACID compliant, which is a very important characteristic of any DBMS. And but yeah, on the other hand,
what does that mean?
I'll get to that on the next slide. Not expected to understand what ACID compliance is, but if you are going to use SQL, right, then you have a little bit more of a startup cost to get everything up and running, as well as it usually uses a little bit more resources to use. Also, scaling it is more difficult horizontally, which is usually the preferred way of scaling something. It allows you to make more cost-effective scaling solutions. So yeah, that's kind of something to think about. But again, as scaling changes, you need to be really current with that. But ACID compliance is really nice. So this is where you start to get some of the benefits of using a DBMS over having the data just stored in a spreadsheet. So ACID is just an acronym, ACID. The first is Atomicity. And I found this picture from BMC on the right, which had really nice, just really good descriptions of these things. And so I had my own, and then I kind of mix and match them because sometimes you could take a long time to explain this stuff, but here it's really simple, right? So atomicity means that you either do a bunch of stuff or you don't. And so there's this idea of transactions, which I'll talk about, where you actually sequence multiple changes to the database. But in general, what you want to have happen is nothing that's left in an interim state. And that means at any point in time, if you pull the power plug on the machine running the database, nothing is broken, right? It has to always be able to be in a state of integrity, right? Or nothing happens. It rolls back the changes. Consistency means that you define rules for the data, and those rules are always obeyed. And if you try to violate them, it just doesn't make the changes to the database. Some of those things could include cascading, for example, which means when you make a change to let's say, a user's ID number, but then a user also has an email, and that's in a separate table, and the email has the user's ID as well, but then the user's ID number is in their phone number table as well, well, if you change it in one place, it'll cascade to all of them, right? That would be a cascade rule. Triggers, constraints, kind of, I would say use your imagination, honestly, that you can just specify whatever you need your data to look like or what you want it to do. Isolation. Isolation refers to, like when you have a database, you don't usually just have one connection to the database. You might have as many as 400 connections to the database all at the same time. For example, when you use Facebook, you're not the only person on Facebook. There's going to be millions of people on the site, and they're all making reads and writes to the database at the same time. And so in order for isolation to work, you need to guarantee that each thing somebody tries to do doesn't affect something somebody else is trying to do. For instance, what happens when you pull up a profile while they're changing it? Is it possible that you pull up a half-changed profile? Things like that should be impossible. It becomes even more critical when you're dealing with things like banking, where you need to add and subtract values, and a computer will store those in memory. And what can happen is that sometimes things just don't behave the way that they're supposed to because you have multiple connections making changes to the same data at the same time, and it just fucks the whole thing up. And so you're balancing parallelization with serialization. So on one extreme, you say only one person can touch the database at a time. On the other extreme, you say everybody uses it at the same time. Typically, you have a balance where maybe a table is locked, or rows in the table are locked, or columns are locked, or you can read concurrently, but you can't do writes, etc. You get the idea. And then durability refers to being able to guarantee that the data will stay there. If the database said we're good, that means that if the power plug is pulled, or you could take this to no end, right? I mean, what happens if the hard drive fails? Well, a good database should be able to handle a hard drive failing. That means the data is replicated over multiple drives. You have redundancy now, etc. But at the very least, you should make it impossible for things that can just generally happen, such as power failures or system failures, to actually affect the data, right? That would be like the most simplest form of durability. And so if it says
and the ability for it to come back up, and how big of a system that is. Because like with my job, if the system were to go down where I work, it would be really bad. And like, it would be extremely complicated to figure out the processing of everything without it. And if it healthcare networks get hacked all the time. Like, I don't really know what that truly means, but they hold it for ransom. People pay because it's healthcare, and they're poor, and they pay out because they have to get it back. So I'm curious. That's key, I think, to durability.
Yeah, absolutely. It's one of the high selling points of using a DBMS is it comes with a lot of extra free perks. I'm not sure, like from hacking, how closely related those are, but it's definitely a part of it, right? If your data's at risk of being lost, you've got some problems, and so part of durability
or
is
just even not accessed. I don't know how the users can access it, but there's got to be some way that's being.
Yeah, that's another part of it. There is a permission system within a DBMS, at least within MySQL, where you're able to say who can access what, and that way, if a hacker comes in, maybe they're only able to make read operations, but they can't make write operations because that user wasn't given the privilege for it, or the operations can be on a per table basis, etc. Right? But
Sure, I'll let you get back to topic.
Sure. No, I like the enjoying the feedback though. It's really good. Okay. So inside of a database management system, at least with MySQL, this is literally what's happening. There might be some small changes with other DBMS, but essentially you have a couple of sections, right? The first part is to handle your connections. And so I mentioned, like, you might have 400 connections at the same time. Well, one DBMS may be responsible for that as a single unit, right? It knows that, okay, these people are connected. They might not be doing things all the time. You can just be connected. And that means that you're on that first block. Then whenever you try to do something to the database, it goes into the parser and also the query cache. And so cache basically is just a way of saying that if we've done something in the past, we'll just do it. We'll reuse what we did before. So yeah, so the parser will do all kinds of stuff. One of the things the parser will do is check to see if we have a cache hit. If it does, then you get high performance. But if not, then it will take your query and formulate it into, well, what do we need from the database? And this is quite a complex operation. Part of it is optimization. Part of it is executing the built-in functions of the query. Part of it is looking at some of the logic from the storage engines, which is at the bottom line where the data is stored. But essentially what you're doing is you're preparing the query so that the optimizer is able to rephrase it to be the most efficient possible. And I'm not sure it makes sense to give too many examples of how the optimizer might work just yet, because it's important to understand the cardinality relationships between tables and things like that in order to really think about it. And if you're not used to imagining how all these tables look, then the optimizer doesn't make too much sense. But at a high level, what it's doing is it's taking many, like thousands of possible ways of doing something and efficiently finding the fastest path so that you get the most performance out of your database. There's a lot of discussion online as to how to cheat the optimizer to make it even better, etc. And it usually doesn't work very well. But the main idea is that the optimizer is just this amazing component that allows you to do complex things fast.
And that's something we don't have to think about using MySQL. Basically.
That's right. You never have to really, well, I guess if your queries are slow, you might want to understand some things about the optimizer, but in general, you don't need to understand how it's optimizing, just what tools it needs in order to make something more efficient.
Okay.
So is this like programmed ways, like, is this AI learning this? Is this some schmuck for a company doing this? Or is this like programs developed that have put into an optimizer, which then like apply to your data?
No, this is, so it's data independent. This is a part of the database management system, right? So as long as you're using MySQL, then you get the MySQL optimizer bundled right in. And whenever you do queries, it'll do that. Other DBMSs, I guess, have like their own flavors, but they all probably work quite similarly.
Okay.
I would imagine, yeah. Okay, so then there's storage engines, and storage engines, I'm still not very good at differentiating these things, but essentially they do a couple of things. They determine what the data looks like on the disk, and they have data values. You can look them up. Here's an example of the MySQL console and me typing in a command which allows you to see what storage engine is on your table. So in this case, it's InnoDB, which is a very popular one. And an important thing about storage engines is that they implement indexes, which are one of the most critical pieces for performance. What else can I say about storage engines? They are on a per table basis. So that third bullet point there is a command that you could use to just change the storage engine on the fly, and the DBMS will manage that for you. And yeah, there's I guess, like, if you really want to get to the nitty gritty of it and look at, based on my data, if you have a lot of a certain kind of a data, then you need to use a certain kind of storage engine maybe, or concurrency is also related to the storage engine. And so some storage engines will allow you to have more features related to concurrency, such as locking rows instead of the whole table, for example. But for all sakes and purposes, you can kind of not really worry about this for your startup phase of a database, and over time, you can switch it. So it's not like this hard commitment that you have to figure out from the get-go. I've never heard of this being a problem to change, but I suppose.
So storage engine takes your human data and turns it into machine data.
Yeah.
Like it's what's actually storing the data on the computer.
Yeah, on the disk. Yeah, exactly.
On the disk, okay.
Yeah.
So then a computer, so if you took that disk, put it in a different computer, it could read it and generate the data. No.
Well, what the storage engine does is it's a way of mapping what's on the disk into what's in the database. So this way you're able to change the organization of it. I'll make a quick example off the top of my head. I don't know if this is real, but it probably is somewhere. So maybe one storage engine will work by using a lot of space, but it guarantees that if somebody uses the maximum amount of, let's say, characters in their name or text fields in their blob and whatever, right, they saturate the amount of data that's allowed for them, that it guarantees that they'll have it, because the storage engine just always says, oh, if you can have a 4 megabyte photo, then we create a 4 megabyte block on the disk for that user. And so this is very fat now, and it uses up more space, but it guarantees that you never have a storage issue with what's already there. All your users will always be able to access what you've given them availability to. A different storage engine might say, no, you know what, we're going to make it as small as possible, and it's going to be even compressed. And so now it's a little bit slower, and maybe you have some issues where you said somebody could have a 4 megabyte photo uploaded, and when they try to do it, your system's full out of space, right? But you can pack a lot more stuff in there. Those would be decisions that the storage engine would implement.
Okay, I see what you're saying.
Okay, so some big questions you can get from this. One big question would be, how is concurrency managed at the server level and storage level? You have multiple connections coming in at the first layer, so this is one part of concurrency. But then at the storage level, you can also have these connections accessing the storage engine at the same time. And so this is very complex stuff. How does the query optimizer work? It's a crazy question. If you want to really throw a curveball at someone, you just ask them how the query optimizer works, and they're going to be talking for weeks. Okay, so a database management system, at least for SQL, will always have this concept of a transaction. And a transaction is a series of commits, it's a set of commits. No, a set of queries which can be committed or rollbacks, or a rollback, and that is a transaction. By default, MySQL will be auto commit. That means when I say do something, it's committed right away. But it doesn't have to be the case. You can run multiple changes to the database in sequence and then say commit, and then the DBMS will go and do them all in one shot. Or not do them all, and that would be considered a rollback. You can also manually roll something back. And in this way, it would allow you to, for example, maybe you're working at the bank, and if somebody says, oh, I want you to extend my account by this much and do this and that, and then you say, you know what, forget all of that. Well, you can just roll back, and now nothing happened. Actually, nothing happened the whole time. Just rolling back puts you on a clean slate. So that's the general idea of commits and rollbacks. And so a transaction is... How does a transaction work? What is the difference? Getting a little caught up in the terminology here. I tend to use auto commit, so I'm not the best at this, but essentially I think a transaction is one sequence, right? But anyways,
you have to commit any transaction to have actually occurred, but you can do multiple transactions and then commit them all at once.
Exactly. Yeah. Yeah, so the application layer is responsible for handling deadlocks. So for instance, two people can make a transaction at the same time, and let's say each of them say, we're each gonna take something from this row and add it back to the other person's row, right? And then so they both lock both rows after making the first read operation, and then now each one's waiting for the other one to finish, and they're just never gonna end. It surprises a lot of people to figure out that actually there's no solution to this problem. You could apply a bunch of mathematical principles in theory and say hey, you know what, maybe somehow there's a way to say, we'll make the bigger one go first or stop the other one, whatever. But actually it's the application's responsibility for just terminating it. And this actually happens very often. Sometimes, for instance, you might go to a store, pay with your credit card, and it just says refused or declined or whatever for no reason apparently. And maybe one of the reasons could be that it actually encountered a deadlock and it's just the system. Sometimes it'll just kill what's happening to open up for the so you don't have a deadlock, right? And even in the operating system, this is how it resolves deadlocks as well. It'll just wait, do nothing, terminate an application. That's how you solve that.
Somebody else has to try again, and hopefully not at the same time.
Exactly. Yeah. Hopefully you don't create the same deadlock twice. Yeah, and then transaction logging is a really cool feature. So we talked about durability before, right? Where you need to guarantee that if you told the user that like you said commit and it was like, all right, we're good, it's committed to the database, and then you pull the power plug immediately after, what you should expect is that there was no data loss. But what would happen if maybe what you've committed to the database is you've said that like everybody with a name starting with the letter A gets this big picture dumped into their thing, and you duplicate the picture everywhere. So you just added in a whole bunch of data into the database, and it takes a long time to do that. Well, do you wait for the operation to finish before you tell the user that the operation was done, that it's committed, we're good? Well, if you did, sometimes you would end up waiting a very long time to get your answer. Some operations take, they could take several minutes. They could take hours. And so what you do actually is it's something called transaction logging. And what that does is it records the transaction somewhere and it makes the changes to the database in memory. Now remember, if you pull the power plug, your memory's gone. But if you've logged the transaction, then the database management system, when it powers back up, will be smart enough to know that because that transaction was logged and the changes are not written to the disk, that it can continue where it left off or restart the whole thing and go through with it. And this allows you to have a database that's very fast and responsive, and you make changes and it's like doing them in memory, but actually it's persisting on the disk and it's resilient to power failures. Some pretty special stuff, actually. Okay, so you have SQL, which includes your queries, as well as DDL, which is part of your query language. And that means, data definition language. And this is an example of what that might look like. So one of the first things you might do with your database is create a table. And in this example here, I'm creating a table called contact us form JSON. And it has some columns, an ID, a date time that it was submitted on, some form details, user IP, user agent, stuff like that. And then there's some constraints. We mentioned before those consistency rules, right? These constraints are defined within the database. So a U index is just the name of the contact us forms JSON ID U index is just the name of a constraint, and what that actually means is defined somewhere else. Unique is a constraint. Unique just means what you imagine it to mean, that if there's two IDs the same, it violates the unique ID constraint and it rejects whatever you tried to do to the database. Same thing with form details. So form details, there's a check to make sure that it's valid JSON. And that's why the table name is called JSON. It makes sure that you can only put valid JSON in that column. It's kind of cool. So this is data definition language. It just kind of falls separately from query language because you use it to create the structure of the database.
This builds the database as a whole, and then each individual kind of table and their movement within it uses the SLQ.
Yeah, that's right. SQL.
Okay. Sorry,
so let's see, performance testing. So there's another aspect that you probably will be concerned with when running a database management system. So you have many ways of doing this. The way that you should start your performance testing is end-to-end, so that you know how long it takes to do something, And then that way, when that number is bad, you then go to further nitty-gritty levels of your performance testing until eventually you're testing the database. Typically, the database runs very fast, so if you're getting crap performance, it may not be your bottleneck, but it can be your bottleneck, especially as things get more complex. And so there's some tools to test it end to end. Usually you use something that tests it like from using HTTP. There's component tools as well, so that would test more individual parts at a time. MySQL comes with a benchmark function, but as you can see here, we can't actually see what my input is, but you can just imagine it's a query. And I tested it for 1 million times, and it executed in 0.41 seconds. And the reason why it did this is because it just runs the query over and over and over and over again. And we mentioned before the idea of caching. So all it's going to do is cache it the first time and then make a bunch of cache hits. And like no database would ever fulfill 1 million requests in under 500 milliseconds. That's not a very realistic performance expectation. And that's why you shouldn't use these built-in tools. But instead, what you should do is profiling and performance logging. Profiling means, actually it can mean two things, so it's kind of a mixed bag, but both definitions are useful. So one thing you want to do with profiling is look at which parts of your queries are taking a long time. And you can do this all built in with MySQL. You can have it spit out analyses of what's going on. I was thinking of adding it in here, but I don't want to go into too much detail on performance. I think it's maybe a little bit too much. But then also, so there's this feature called performance logging, which means that when queries happen, it just records how long it took to execute them, like inside of the database. And that way, if sometimes, maybe you have a website and your users are reporting, sometimes the performance is bad, well, you can look at your performance logging and determine, oh, actually, like when these conditions are true, we get bad performance. And then now you can do profiling on those queries and see why the performance on them is bad. And this is a very effective way of testing your performance. Now you have some good tools. And on the subject of benchmarking, so what do you do if you want to test, like, how many queries can my database handle? Like, how many users can we handle at one time? Well, the correct solution to this problem is to record real data and then replay it just in fast mode after. And that way you have a nice mixed set of queries and things happening that reflects what actual real users might do. And you get something a little bit more closer to how it might look when you actually have that many users. All right, performance optimization. This is a really fun topic because it's just really cool how fast some of these things can work. And yeah, optimizing a poorly designed or badly indexed schema can improve performance by, I'm not sure what is actually behind the screen there, but I think I said multiple orders of magnitude, 2 orders of magnitude. I've done this with Lawyer Central. There were some queries that were taking several hundreds of milliseconds, and then they could go down to even single-digit milliseconds, or even thousands to double digits, right? This is a very realistic change to have happen. And it's also responsible for stuff like, a lot of people ask this question. You go to Google, you type in anything, and you get millions of results in milliseconds. How does it search the entire internet in 20 milliseconds? How is that possible? Well, indexes are why that's possible. And so when you're optimizing performance, you have two places. You can do it in your query optimization, which is what are you requesting from the database, or your schema optimization, which is how is it structured inside of the database.
So that's the data system, like your little table that you showed us, rather than the query is the structured one.
Exactly, yeah. We haven't seen queries yet, but that's right. The DDL is where we define the schema.
Okay.
Sometimes people create or use these systems that make managing the database easy because it does it all for you. Some of them use something called object relational mapping. where objects in your code are replicated as database objects. And unfortunately, they can cause some really bad performance issues down the road because they don't scale well, and the system isn't able to know where to put indexes or how to structure it so it's optimized for better performance. And then it scales poorly when you need to build more up. So they're sold as something that abstracts complexity, but actually it ends up you have to pay for it later. And it's just something to be careful of. That there might be some systems that are smarter today that can do that, but I imagine there's also new systems that don't optimize for performance. It can be a problem. So schema optimization. The most effective thing you can do is indexing. Indexing means that if you have, let's say you have some tables. Let's make up a database, right? Let's say you run, well, let's talk about the Lawyer Central database. That one should be easy. So we have lawyers, and lawyers can have phone numbers and email addresses, right? And you might want to, and they have locations, and they have fields of law. They have all kinds of stuff. But they don't all have all of these things. And so what you do is you set up your tables so that they're separate. So the phone numbers are in one table, the lawyers' names are in another table, and that way not every lawyer has a name, but not every lawyer has a phone number. So then that way we don't need to have like a null value if it was a phone number column in the table with the name in it, right? You just say, oh, okay, well, if it's in the other table, then we have it. Okay, so that's fine. So that exists for their field of law as well. Now, if you want to find all the lawyers that practice a certain field of law, what you need to do is go into the table that says the lawyer ID number and the field of law that the lawyer practices, and find all of those fields of law. And if you don't have an index, then what that will mean is that you need to manually search through the entire table to find out where the fields of law are. Emil, you might have remembered the challenge question we worked on a while back there, where I mentioned the idea of a dictionary where you're able to do instant time lookup. That's how the index works. The index is a dictionary for a database. And so what it does is it says, oh, you need this field of law? We already calculated where all those rows are. You don't have to do any work. We already know where they are. We did it ahead of time. So you pay by using space up on your disk to store this information, but then when you query it later, it's instant. There's no lookup time. It's not searching for it. It already knows which lawyers are practicing that field of law. And so indexing is insanely powerful for performance, right? That's how Google will say, well, how does Google know that when you search for funny cats, instantly it knows which sites those funny cats are on? Well, it takes funny and cats. Those are keywords. It takes the data, the websites that it searches for, and it puts the keywords in a database, but it indexes the keywords. And now when you need to find which websites have funny cats on them, it already computed that. It knows it instantly. It doesn't need to search for the funny cat ones. It just says, you wanted funny cats, we already did it. So that's how you get it in like 20 milliseconds, even though there's billions of trillions of websites. Probably trillions.
So is this something you set up again in the database that you're setting up? Like, are you setting up how it indexes?
Yes. Yeah.
Are you doing that with, I guess, the database management system then?
That's right. Yeah, you set it up with your... I can give some examples after, actually. I'll go into some detail about what setting that up kind of looks like. But essentially, you just define what your index is. So you can index on any column.
Okay.
Yeah. Optimal data types. Smaller is better in this case. That means that I mentioned the idea before of a storage engine using up all the space available. And this tends to be the case, even in memory, right? That if you say users can have, 4 megabyte photos, then it takes up 4 megabytes regardless of whether they use that or not. Some storage engines might have more efficient solutions to this, but it happens everywhere. If you have a phone number space and you allow them to put 160 characters in there, then it just uses up a lot of storage. When you scale that up to millions of users and they're all using 160 characters for the phone number slot, it can add up to a ton of wasted space on your disk, right? Because the data, or in memory, depending on the particular storage engine and how it's optimized. It's not, I don't think it's true to just say that because you've said that it can use that much, it's wasted. But some things, for example, an ID number. Well, you could, if you were a bad admin, you could say the ID number is a string, even though you're putting a numerical value in there. And that's bad because integers are much smaller. It's easier to represent integers than it is strings, stuff like that, right? Smaller is better. The more efficient you can put your data types, if you know already that max that can go in there, then you say what it is. In fact, you always have to say what the maximum for anything is, right? Usually you're just, I don't know what the biggest name somebody could have is, so you allow it to be 28 characters and just hope you never need more. Minimize the number of CPU cycles needed to access data. This means that, sometimes queries can have mathematical operations in there. Find me all the users that have clicked this button in the last 3 days. Well, that's complex because now you need to compute what are the last 3 days and then find all the users who click that button. And it takes more CPU cycles to do that than it is to just find maybe all the users who've logged in the last 3 days. You don't need to query the other table maybe, or I'm not sure. I'm not very good at making up these examples on the fly, but sometimes the CPU cycles can be like transformations on the input that the DBMS can do, but why would you do that? You can do it before it gets to the DBMS. And avoiding null values. So yeah, you can have null values in your indexes. It's just something you shouldn't do because what does that even mean? It's indexed based on this and you search by null value. It's something that can happen. Null values will be a theme we'll talk about in a moment here. But yeah, indexes. So a small, lightly loaded database will perform well even if it's poorly indexed. But as the data set grows, performance will drop quickly. And that's just the way it is. Normalization. Normalization, yeah, I deliberately didn't write much on this slide because, you have first normal form, second normal form, third normal form. I think it even goes up to like sixth normal form now. And what it means is with each higher degree of normalization to your database, you have more constraints that are just always true. So in one of these normalization forms, you say, for example...
What does normalization mean, though? That word.
Normalization is a way of standardizing what's in the data. So I'll give some examples. It'll make a little bit more sense. So if your data has... Remember I said like you could have lawyers and then they could have phone numbers, but they might not all have a phone number. And so if the phone number is in the same table as the lawyer's name, then you're going to have null values in there. And this has not been normalized for their phone number because it's one of the rules that you're just not allowed to have null values, right? So if you don't want to have null values, you need to put the phone numbers in a separate table. And now you've normalized the phone numbers. But the normalization can go to much higher degrees where they talk about the relationships between the data. And the effort for this is to maximize performance and minimize duplicated information. Another form of normalization is if you have two pieces of data in one cell. For example, what if a lawyer has two phone numbers? Well, it would violate one of these normalization levels if, and you can find them on Wikipedia, they're all over the internet, but if a lawyer is allowed to input two phone numbers in the phone number slot, well, now when you're searching their phone numbers, you might get these weird anomalies in the data where there's actually two numbers in there, and that would violate a normalization. In fact, if you wanted to solve that problem, you need to allow your phone number table to just have multiple numbers for the same lawyer in there. So all of this stuff, why do we do it? Why do we even care? Well, on the one hand, normalization is nice for geek metrics. You can sort of say, oh yeah, my database is super pure and it's holy and wonderful. But the reality is, from my experience, oftentimes you don't want to try to take this too far, and it really shouldn't be something that an admin strives to, oh, we have to make it third normal form, because in a lot of cases, yes, it'll be more performant. Yes, it'll save wasted disk space, etc. But there's business needs that you have as well. Is it convenient? Are you wasting time with this stuff? Is it providing value to your customers to split it up this way? Because maybe they don't care, and maybe it's just easier for you to manage it with letting multiple phone numbers be in that field. You know, it could be a thing, right? So
normalizations are standards then.
standards,
Best practices.
Yeah.
Okay, I see. So
They exist, but they don't exist in reality.
Yeah, they're theoretical constraints you put on yourself.
Right.
Yeah.
Okay. So I guess the degree of normalization is the degree of how good your database is conforming to
Exactly.
industry standards. Okay.
Yeah, exactly. So it's good to be aware of them and to understand how do I best structure this. But if you always try to make it too perfect, sometimes it's just not practical. It's easier to, like, for instance, I made a slide here before this one where the details of the user's form are just a JSON object that I dump in the database. That I don't know if this would violate normalization, but it probably would somewhere, since the JSON object is the same shape every single time. And so technically I should have made a separate table that says, you know, what are all the details of the submitted case. But I wanted to make this future proof and say, well, I want to be able to change it whenever I want and not care about that. And so I violate, probably, I don't even know if it's a normalization law, but I would imagine it would be one of the higher levels of normalization would say, if you have this structured data, you shouldn't be dumping all that in one cell. I don't care. It's not providing value to anybody to have it that way. So that's the idea of normalization. It's typically something that will be talked about at maybe data engineering job interviews, or geeky metrics for, if you want to just brag about how great you are at setting up a database, you can say that it's third normal form. Okay, so database schema. The schema includes, like what you create with your DDL. And the first layer is the databases. Remember, the whole time we've been talking about database management systems. One database is just a collection of tables and rules and maybe views and stuff like that. But you can have multiple databases in the same, let's call it namespace, if you will. It's pretty common for systems to just make a bunch of databases and then distribute the data between those databases, especially if there's no relationship between one set of data and another. Just because they're part of the same company doesn't mean they all go in the same database. Maybe think of it as using a separate Excel sheet, for example. So tables are where you put the data. Columns are the things that can go inside of tables. Foreign keys are special columns. And so kudos, Colin, for reading up on this ahead of time. A foreign key is a constraint that you put on a table. It's one of the things the DBMS will ensure is always true. And so in the example of the lawyer's table and the lawyer's phone number, the phone number would have a lawyer ID and a phone number, and the lawyer ID is a foreign key to the original lawyer's table, which gives the lawyer their ID number. And that way, it's impossible to have a phone number that doesn't correspond to a lawyer. Like their ID number doesn't exist in the other table. That's impossible if it's a foreign key. And that's again where those cascade rules comes in. If you changed the first lawyer's ID, it will automatically follow whatever rule you set for the ID in the table with the phone number.
So is a foreign key that thing that makes the relationships between the tables?
No,
exactly.
That's the primary, isn't it? The primary is what, then the foreign key is what relates back to the primary. So if the primary is the lawyer, the foreign is the phone number. Or do I have that inverted? But I know if you can be either, but.
Well, you don't need to reference a primary key with your foreign key. You should.
Okay.
It's a good practice. It's a good practice to do that, but a primary key doesn't necessarily. A primary key is a way of uniquely identifying. It's like your core thing in your table. right? So for instance, you know, in the example of the lawyers with their name and their ID number, you could say it's primary keyed by ID number, because ID number means that now we have the number, we can find the lawyer. You know, it has to be unique. That's all good. But you could say it's primary keyed by their first and last name. That's also a valid primary key. It means that now you can't have two lawyers with the exact same name in that table. That might be a good thing. And so in that way, it will typically, you know, a lot of these user interface systems will automatically index a table by its primary key, because well, if that's what you identify your stuff with, then you can set up indexes on those columns and quickly look up the data that you need. Make sense?
Okay. I think so.
Okay. Yeah, and we can revisit that as well. So indexes, right? Yeah, you know, something we've talked a lot about already, right? You just define which columns are indexes. One of the things you can do with an index is say like it's indexed by ID ascending, and that just refers to how it's indexed on the disk, right? It could be descending, ascending, that kind of thing. Integrity constraints. An integrity constraint might be like where I mentioned in this table here. You see here constraint check JSON valid. That's an integrity constraint. It forces that data entry is valid JSON. And default values, another thing that you define in your schema. A common default value is the current time, date created. Pop it in there, right? The DBMS will create that. You don't need to feed when it was created to the DBMS. In fact, you shouldn't. Yeah, so ERD. So if you type in database on Google Images, you'll probably see a lot of stuff like this. This is an old ERD for Lawyer Central, and it starts to demonstrate the complexity of tables and what they look like. It's kind of an annoying thing actually to look at. But on the other hand, it demonstrates a lot of the concepts we've talked about already and what they look like. So you can see that table in the middle called lawyer has a lawyer ID, a first name and a last name and a created on. And then they have stuff. They have phone numbers, they have email addresses, websites, things like that. And you'll notice there's a little icon between the like the edges of the arrow. And sometimes it shows the 3 prongs going out, and sometimes it shows the 2 dashed lines. And this refers to the cardinality of the relationship. And so, as you mentioned, you need a foreign key. But what you can also do is you can set up that, for instance, if lawyer phone is primary keyed by lawyer ID, what that means is that you can't have one lawyer with 2 phone numbers. It's a one-to-one relationship now because you can't have 2 of the same lawyer ID in the lawyer phone table. But if you say, okay, instead I want it primary keyed by lawyer ID and phone number, that means one lawyer can't have 2 of the same phone number. Well, that makes a lot of sense, but you've just changed the cardinality. Now it means that you have a one-to-many relationship. So as in one lawyer can have as many phone numbers as you want, unless you've put further constraints. And these relationships are very important for the query optimizer. It's very important to understand which is one-to-one and which is one-to-many and which is many-to-one and etc. Because you get a fan-out problem that you want to make it have. You want when you're actually querying this stuff, you want it to have the smallest amount of data as you go through until you get to the very end so it doesn't explode. You know, for instance, if you wanted to get all the lawyers, you don't start with the phone numbers because there's multiple phone numbers and you have to connect them all with lawyers. No, better to start with the lawyers and then get the phone numbers because it's one-to-many, that kind of a thing. And so on the right-hand side here, you can see some of the details. So there's like the yellow key is the primary key thing. I'm not sure why the foreign key isn't showing up. This was using old junky software. Not sure if there's like one foreign key there in the middle. Lawyer field of law field is foreign keyed. It should be like that orange diamond. And anyway, so you just have some representation. This is a really common way of looking at what a database looks like visually. How do you represent it, and how do these relationships connect with one another? Anyone who's building a database
almost like a schematic.
A what?
Schematic? Can't say the word. Schematic. Yeah. Oh my God, I give up.
Schematic.
Schematic. That's the word. Yes.
Yeah, it has most of the information, and it's nice to visualize. It gives you a good idea of. Oh man, I can't. There we go. Let me remove this. Okay. Okay. Yeah, it gives you a nice idea of actually what the data is doing. Yeah, so SQL joins are a very common query. So joins are what you use to add multiple tables. Like when somebody gets a lawyer's profile page on Lawyer Central, they're doing joins with the lawyer, like the ID number, and all of those other tables that were connected there. They're all joined. And so it's kind of fun to look at the union algebra. I can go through the examples, right? So in the first one, like let's say table or like circle A is the lawyer with the first name and the last name, and circle B is the website. And in order for this example to work, I have to assume that we have websites for things that are not lawyers. Let's say you have lawyers and doctors, and they can each have websites, okay? And in A, it's the lawyers, and B, it's the websites. Well, in the first table, you're saying, give me all of the lawyers, and if they have a website, give me that too. And the white part are the websites that are not for lawyers. I wish I could put here, I'll just close this so you can see my mouse. So in this one here, what you're saying is, give me all of the lawyers who do not have websites. In this one, you're saying, give me all of the lawyers and all of the websites. In this one, you're saying, give me all of the lawyers who don't have websites and all of the websites for everybody else that are not for lawyers. In this one, you're saying, give me all of the websites that are not for lawyers. In this one, you're saying, give me all of the websites that lawyers have. And in this one, you're saying, give me all of the websites.
And is this an example of a query?
Yeah, these are all query examples here. They're join examples, right? So, typically this would be a part of it is a query in and of itself. The whole query is written right there. But typically you use these in conjunction with, like you're looking for more than just one thing. But technically, yeah, it's a valid query.
So this is often kind of reminds me of like when I'm searching for scientific research papers and you're able to enter various like keywords, and it's like you can search this and this or this, and
Yeah.
It's kind of how you search to try to get as little results but the most specific.
Exactly. This is how they're implementing it on the database side. Exactly this.
Okay.
Yeah.
So this would already have to be pre-coded for someone then to search these.
Oh yeah, exactly.
Okay.
Yeah, I'm going to show an example of that too, right? I wanted to go into more detail with that actually. Yeah, so query language. So let's dive, we talked about DDL. There's also queries. So these are all queries here. So select phone from lawyer phone where lawyer ID equals question mark. And what this query does is it gives you the phone number for a particular lawyer. You can insert, you can delete, and you can update. And all of these are pretty much the same, except for the insert. You need to include two values. It's the only one which has actually both. I guess update actually has two values as well, because you're saying set the phone number to this where the lawyer ID number is that, right? That one also has.
Does question mark here mean like just an arbitrary?
It'd be the ID
value?
of the person.
Yeah, it's actually a placeholder, right? So in the code, actually, in certain libraries that you use to execute your query language, you usually have this idea of putting in placeholders, and then you fill it in with variables. And so this is actually copy pasted directly from my code. I didn't add the question mark in. That's literally the syntax for it. But you might have different syntax for placeholders.
It's almost like an X value.
Yeah, exactly.
Because it varies per like everybody. Like
Yeah, whenever
every
you run the query,
information
right?
set.
Yeah, like what are you searching
Okay.
for? Like usually like if you're searching for articles, you'd say like where the name looks like this, and then this is the question mark, you know, and that's your search query. So a complex query. So those are simple queries. They're just one-liners. But actually, I've got what a complex one looks like, and so this is one of the main Lawyer Central queries that we use. And what you're doing is you're selecting data. So these are the select statements right here. So it goes from select and from. Remember in the basic example, you had select this, where this, from this. I'll actually quickly just go back to that, right? So we can see. So select phone from table where condition, right? This is a very reusable template. So here we're having select. We're selecting all of this. Actually, is that? Yeah, it's just indented poorly. But this is what we're selecting, right? So we're getting the name, the ID, the postal code, the latitude and longitude. We're formatting the date. We're having things, if they're null, what do we do? There's some conditions in here, but this is the select part of the query. And then when we go down, we have the from, and that's where those join operations happen. So from, lawyer, join, we have a subtable for a field of law. A subtable is just a query within a query. You typically don't have all your data perfectly in tables. You know, you need to query the table for some special conditions. So join this table, join this table, join this one here. You're doing a query and aggregating as a JSON. One thing you want to be careful of is, remember, so like one lawyer could have multiple phone numbers, but you want them to exist as nice rows when you get your output. You don't want to have like 3 rows for the same lawyer. So you have to aggregate those phone numbers somehow. Well, one way of doing it is with a JSON object. In this case, we're aggregating the reviews so that it's a big array of objects. That's why it looks complicated, and it actually is. It took a long time to write this, but that's part of the complexity of databases. You know, remember, a review isn't just it's not easy to just grab that data, right? They each have their own rows of their own. Anyway, so you go down through here, you have join, 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 and then finally where condition, where lawyer ID in, and then question mark. In this special query, it's in, because you can do it for multiple IDs at the same time, but it could just easily just be like a where lawyer ID equals if you just want to have one.
So this is implemented in what language? JavaScript?
Yeah, so the library is JavaScript, but this is query language here. So this you could pretty easily just copy paste this into an SQL terminal. The only thing that you'd need to do is replace the placeholders with the actual ID numbers.
I see. So is JavaScript, in this case, it has a way to interface with structured query language? Is that the idea?
Exactly, yeah. There's a library where you make a connection to the database, and it allows you to execute your queries.
And do all or many languages have a library that will let you interface with structured query language?
Yeah, it's a very basic feature. If a programming language doesn't have this feature, it's probably because the language is not really used, or it's very low level, like assembler wouldn't have that, but you know, that's some pretty niche stuff, right? But this is, yeah, a really basic feature for a programming language.
I see, and they're all going to use the same kinds of templates, like left join, select, from, where.
Well, that's not programming language dependent. That's dependent, if you're using SQL, you're using all of this.
I see.
Yeah,
okay.
That's a feature of SQL, right? That's what makes it beautiful, is that it's, you know, if you know it once, you know it for every programming language.
Okay.
Yeah. Okay.
Neat.
Yeah. Oh no, I didn't want to. Oh, you can move this? Cool. Okay. Play.
Yeah.
All right. Yeah. So that's an example of a complex query. That's a very big query. It's like 200 lines. You know, it takes a lot of work to build those, but that's what's happening. Let's say when you load up like a Facebook profile, it's doing these complex join, getting all the data, right?
So of course you write it once, make sure it works, and then you can just run it over and over again.
Yeah, exactly, right. And so, and that's where I think I'll show you guys a little bit more. That I'm not sure if I'll put it in the YouTube video, but what all those statements look like in the code side. But at the very least, what I can talk about already is the architecture. And so typically you have, I'll just make this smaller for a second here because I want to use my mouse to point. But you have a front end. So maybe it's your phone, your browser, etc. Then that connects to an API, which is part of your backend. And your backend, not crap. Crap, we ran out of time again. Okay, we're back here. All right, that was quick. Okay, so yeah, so you have your front end, and then it makes API queries to the back end, and the back end will have three components: routes, controller, and model. The routes are the API. It's what does the front end use to communicate with the back end, or I guess technically, when I say front end, I could be talking about an app on your phone. It could be a website. It could be something you run on your computer. Whatever it is that's calling those API routes, that's probably your front end. And then so the routes are what you query. Then those go into a controller. The controller is what runs the database functions. So that thing that I showed you, that complex query, that's part of the model. And you write the query once, and then every time you need that, you call it in your controller. And so the controller might combine these, or it might make changes to what the user's data was, or validate it first before trying to make the queries on the model. And that's how you see it here. So maybe the front end will say, I want to do this thing, and then it calls the API, and then the back end will, the controller will like sanitize that or figure out which, stuff it needs to do to the database, and then the model will actually execute those queries within the database, and then quickly get out of there to free up the database for other stuff and return that content back to the front end or confirm that the changes were made.